Hello and welcome to our final demo video. We are the WattsWatch Power Logger. We are group number 23 for Senior Design Summer 2025. Our group is comprised of 3 electrical engineers and 1 computer engineer, and this project is sponsored by Echo Ed Corp.
So this is our project installed in a panel. It's put in the panel right now. It's not 100% organized because this panel is too small compared to what we had initially thought about to install our panel. But we have 3 CTs. Each one is going to this integrator on this input side, as you can see in here. And then we have the 9-volt DC power. Those 2 wires go through the shades that we install in here and connect to this portion right here, which is fed from the 5-volt to 9-volt regulator, and this powers this integrator. From here, from this input, then we go to the output, which goes back to this shades that we have in the panel, and it comes to phase 3, phase 2, and phase 1, and this sends the current signal to our website. Then we also have 4 wires for 4 alligator clips coming to each one of the phases and the neutral. These wires feed all the integrators and all the board through this voltage transformers. We have a 5.5 volts to the 3.3 regulator that feeds the ESP32 and the previously mentioned step-up regulator to the CTs. So altogether, this is a project that's working. Again, this design is not how it was designed to be installed, so that's why it looks a little bit disorganized.
So this is our website. We have a login page, a sign up page, and then we have a page if you forgot your password to reset it. So I'm going to log into a previously made user. Actually, right now I'll just show you. This is the wrong password. It'll give you an error. And this is the right password. So I'm going to hit download PDF right now because it takes a little while to compile everything. So our dashboard here, we have phase 1. We're in phase 1 phase mode right now. We have phase 1, phase 2, voltage, current, power for all of them, and line 1 to 2 voltage. So we can switch to 3-phase mode. It adds a whole new phase, voltage, current, power, and each line voltage. And if you wait, you can see here that every 5 seconds we'll get a new reading. So let's look at the report. So on the first page, we have the all-time peak values for the last 30 days. The data was generated, and all-time peak values forever. And as of right now, these are the same because we only have about 4 days of data. As you can see, 718 to 721. So these are each voltage for each phase, currents for each phase, power for each phase, and each line-to-line voltage. Here's the daily peaks for the last 4 days. And this is why it takes so long to download. These are every 15-minute peak reading for the last 30 days. But as of right now, it's only 4 days. And this is a requirement for the NEC. So I want to show you the database. So we have 3 collections. We have readings, saved readings, and users. Users obviously store the login and password for each user, but obviously it's encrypted. And the readings is just the real-time readings. So these come in every 5 seconds. And we could change that too if we want. We have a 5,000 millisecond delay as of right now, but we could change it to 1 or whatever you need. And save readings is the 15-minute peak readings. So these come in every 15 minutes. And I'll refresh here just to show you that these the documents are, the data is coming in. We get more documents now. And I just wanted to show you how much this can store. So we have the free version of MongoDB. Each document size is about 298 bytes. So we can store 1.7 million documents. And that gives us about 100 days of data. So that is well above 30 days. But if we were to buy a better version of MongoDB, we could store up like years of data.
Here is our project fully finished in its casing. We start up here with the input from the panels, 120 volts, leading directly into the 3 voltage measuring circuits. Here on the right is the power supply that turns the 120 volts into the usable 5 volts 3 amps. Over here on the left hand side is the 3 current measuring circuits. Here in the middle is the MCU subcircuit. Down here on the right hand side is the space for the battery backup system. Here is the 5 volt to 3.3 volt regulator. Right here is the 5 volt to 9 volt regulator. Here is the space for a 5 volt bypass, so we can power the system and do testing without connecting to the panel. Here is the AC input signal bypass, so that way we can mirror here on the voltage measuring circuits the same signal that it would receive right after the voltage transformer. This was used for testing. Seen here is the 5 volt to 3.3 volt regulator. Currently it is off. The LED is also off. I'm going to turn on the power. 5 volts in. We are reading good output power. The LED is on. And here on the multimeter, we're reading 3.3 volts out. Here is our 5 volt to 9 volt boost switching regulator. Currently it is off. There is no power running to it. The LED is off. I'm going to input 5 volts to it. Regulator is now on. The LED is illuminated. And then coming over to the multimeter, we are at 9 volts. Thank you to our sponsor for hooking up our device to a panel. This shows that the panel alone and subsystems to power the MCU and everything are properly working. We can see the MCU giving out the LED signals, and the LEDs on the 5 volt and to 3.3 and 5 volt to 9 volt regulator are properly functioning.
To calculate the current circuit gain and the voltage circuit gain, we provided different inputs to both of them of the values that we expect from the real world, and some of the values that are a little bit farther off to make sure they maintain their linearity. For the current circuit, we provided 5 inputs ranging from 0.01 to 0.05. As you can see on the screen, it provided a graph that was completely linear with a slope of 19.21. So we ended up using that as our gain for the current circuit. For voltage circuit, we provided 5 inputs as well, ranging from 0.1 to 0.3 with increments of 0.05. We also got a linear graph on it, and our slope was 4.65, which we ended up using as the gain for our circuit.
Seen here is our first voltage test. On the left-hand side, you can see the time and date and that the program sees. It's the same time and date that the computer sees, meaning that the 2 times are in sync. The next column over is the ADC value that the ESP32 is seeing, including both the AC and DC offset. Next column over is that DC offset that is brought about by the voltage measuring circuit. The next column over is the AC portion only that the ADC is seeing. This is the signal that is seen after the voltage measuring circuit. The next column over is the original input signal, and we are receiving that through the output signal, and after doing some calculations on it in the code, retrieving the original signal. In this case, the original signal was 100 millivolts. Seen on the screen is the second voltage test. We inputted a signal of 0.136 millivolts. We use this exact signal because through testing in the lab with Dr. Weeks, we saw that with a supply of 120 volts, after the voltage transformer, we were getting 136 millivolts. So we wanted to run this test as accurately as possible. Seen here is the third voltage test. We had an input signal of 190 millivolts, and we were getting very close values. We were getting 187, 186, up to 188, so very close.
As seen on the video, we use a signal of 33 millivolts, which corresponds to about 10% of what the total output signal will be from the CTs. By doing the calculations as shown in there with the RMS at the ADC and the DC offset, you can see that the ADC being read by the MCU is the value that we're expecting based on the initial signal. The reason we did the testing without connecting directly the CTs to the panel is because the CTs have already been tested, and we know that the value will be between 0 and 0.33 volts. So we decided to disconnect our board to a function generator and test it that way for simplicity. This is the second test for our current circuit measurement. As you can see on the screen, the original signal RMS is 0.047 volts. Our input was of 0.045, so while it's not exact, it is within our well within our limits. For our third test, we supplied an input of 0.06 volts to the board. We were reading a value of 0.058 as is shown on the screen. So while it's not 100% exact, it is within our allowed percentage.
We will be testing 3 specifications in this video. First is our maximum input voltage, which will be 120 volts per line. Second is accurate timekeeping, which will have less than a 5-second difference from the global clock. And last is accurate voltage measurement at less than 15% error. As you can see, there's only a 479 millisecond delay. And that was 250, so it's within 1 second you're getting these readings.
Here is our product versus an established product that is already on the market. Here on the right-hand side is the established product that is used as a removable option for taking those 30 days of continuous data and then removing it and moving on to the next panel, versus our product, which is designed to be a installed permanently option. It's a little disorganized because there's 2 different loggers installed on this panel. And here is our readings versus the established product's readings. Over on the left is the voltages, same here. And then in this middle column, the currents for each phase compared to the currents that it is reading. Here's the line-to-line voltages versus the established products line-to-line voltages. Here is our readings of the WattsWatch versus an already established reading from the PEL 103 meter. For phase 1 voltage, we had a total percent difference of 0.191% over the total average. For the current, 0.182%. For phase 2 voltage, 0.229%. For phase 2 current, 0.202%. For phase 3 voltage, 0.181%. For phase 3 current, 3.273%, which can be explained because the readings are in the milliamp range for both of the readings. Overall, the average current and voltage readings were well below our 15% difference goal for our engineering specifications.